All right, tonight we will be discussing about vertical non-uniform circular motion. And I will be presenting one problem in order for you to somehow practice how to calculate the unknowns of our vertical non-uniform circular motion. As we all know, when we say non-uniform circular motion, the speed is not constant. Therefore, it will change at any point of our object around the non-uniform vertical circular motion. And we will be focusing here. Speed is not constant. The motion when the object is going down. Say, for example, in our vertical circular motion, the speed increases along the circular motion. So when the object will go down, let's say for example from here and then go down to this direction, the speed will increase. And then uh, on the other hand, if the object is like going up in our non-uniform circular motion, the speed decreases due to gravity. I guess these are the things that we need to know in discussing vertical non-uniform circular motion. But we will focus on one problem that we will be discussing now. Again and again, in our non-uniform circular motion, the speed is not constant. As it goes down, speed increases. As it goes up, speed decreases. A mechanical object of mass 0.75 kilogram is attached to a high-strength tether of length 2 meters. When you say tether, it could be a rope or a string. Again, stuff like that will act as our centripetal force, or that will generate or produce the centripetal force. The object is launched into a vertical circular path, and in this case, we will be dealing the non-uniform circular motion. Therefore, speed is changing. Okay, it's a vertical circular motion. Imagine a Ferris wheel mechanism wherein the circular motion is done vertically. All right, this time it's not a Ferris wheel, it's a tether or a rope or a string attached to this mass of 0.75. At one point during its ascent or going up, the object is moving at a speed of 4 meters per second, and the tether makes an angle of 86 degrees with the bottom vertical. Figure out the tension in the tether at this exact moment. So as it ascends, as we all know, the speed is going to be decreasing as it goes up. And we have a given 4 meters per second, a snap uh, velocity or speed in this particular angle, 86 degree with respect to the bottom vertical. So it looks like this. If this will be our circle, and we have our center point here, and this is going to be our bottom part, the bottom part here, and our object is at 86 degrees with the bottom vertical. So if we will try to set our bottom as 0 degree, so from 0, and then let's pretend that it's this is our 90 degree here, 90 degrees, and then let's say this is where our object is at the moment, and let's say it's 86 degrees here, let's assume. And as we all know that there is a tether force here towards the center generating the centripetal force, and since it involves string or rope, the tether itself is a string or a rope, so this is going to be our tension force. T means our tension. Okay, and the tension produces the FC or the centripetal force. So it will, the arrow or the vector is going towards the center point of our circular motion. Okay, and everything that will point towards the center, points to center, we can assign positive as the convention sign. And pointing away or point away from center, it's going to be negative. Okay, so in this case, our centripetal force, which is generated by the tension force, it's positive because it is going towards the center of the point. Okay, so let's try to find the tension force in this particular moment at 86 degrees with respect to the bottom, vertical, and then we have a velocity of 4 meter per second, and the mass of also of our object, it's here 0.75 kilogram, and the radius is 2 meters. Given our variables here, we have the mass that is 0.75 kilogram, and we have the radius of our circle from that point 86 degrees with respect to the bottom vertical uh, part, and it's going to be 2 meters. Then we have a theta or angle theta of 86 degrees. And of course, we have our velocity, which is our speed, meter per second, 4 meter per second. And remember, it's a non-uniform circular motion. So our speed here will change, not constant. To get the tension force, the safest formula to be used is this one. Tension is equal to the centripetal force plus mg, then we have the cosine theta. Fc is our centripetal force, or the force being generated because of the tension force or the tether in our circular motion. So we can break down Fc into its original formula. Remember, Fc is equal to mv squared over r. So we can put it here. Instead of Fc, we can have mv squared over r plus the mass and gravity cosine theta. Remember your gravity here, do not make it negative 9.8 meter per second squared. Please remember, do not make it negative. We will get the absolute value of it, which is 9.8 meter per second squared, to be the value of our g, not negative. This time, let's substitute the given. The tension force, we have m. M is the mass, so put it there, 0.75 kilogram, multiplied by the v, or velocity, which is 4 meter per second, and squared, do not forget. Then we have our radius, provided in the problem, it's 2 meters, plus the mass, still the same, 0.75 kilogram, then multiplied by the gravity, 9.8 meter per second squared. Again and again, do not use the negative gravity. Okay, and then we have the cosine theta, which is 86 degrees. Okay, let's get first the centripetal force of our problem. Centripetal force, don't forget that you will do it this way. Copy this 0.75 kilogram multiplied by 4 times 4. 4 times 4, we have 16, because we squared it out, and then meter squared, second squared, divided by 2 meters. So we can cancel something here, like our meter, and then since we have 2 meters here, we can cancel the meter. Okay, so let's continue. Plus, and all you have to do is to input this one in your calculator. So let's have 0.75 multiplied by 9.8 positive, the absolute, the absolute value of our gravity here, times the cosine. Press your cosine button in your calculator, and then plug in 86. And the answer is 0.51. Okay, and the unit here, take a look at kilogram and meter per second squared. This is dimensionless here, so no need to put degree. So kilogram meter per second squared. The remaining unit is kilogram meter per second squared. Next, we're not yet done. We need to divide the product of 0.75 multiplied to 16. So 0.75 times 16, the product is 12 kilogram meter per second squared. And then let's divide it by 2. Copy. 0.51 kilogram meter per second squared. 12 divided by 2, it's 6 kilogram meter per second squared plus 0.51 kilogram meter per second squared. And let's add these two because we have the same units here. So it's 6.51 kilogram meter per second squared. Okay, or this kilogram meter per second squared, we can write it as 6.51. Instead of kilogram meter per second squared, you can just write Newton. This is the tension force when our object is here at 86 degrees with respect to the bottom part. So the tension force here is 6.51 newtons. Now another condition here, the continuation of our problem, the same object with 0.75 kilogram mass, and the radius of our vertical non-uniform circular motion is 2 meters. And we got the tension at 86 degrees using that certain formula, and we arrive that our tension force is 6.51 newtons. And this time, let's continue. As the object continues to climb or ascend, the engineer notes that its speed is dropping critically due to gravity, and it's expected because as we go up to our loop, our speed, of course, decreases. Let's not forget. And then, what is the minimum critical speed the object must maintain at the very top of the loop to prevent the tether from going slack? When you will encounter the word slack, it's just like losing the tension, or the tether is losing its strength, for example. Okay, so what is that minimum speed that is needed at the top part? The top minimum speed, what is that? Or what's the magnitude or the value of our top minimum speed that is needed in order for our object to like fully pass the top of it without losing tension or going slack? Okay, so how are we going to answer that? Let me clean this mess for a while. At the top of it, we have our derived formula as we follow the Newton second law, and we got this formula here to get the minimum speed at the top. Hold on. The formula is velocity at the top, and that will be minimum is equal to the square root of gravity and then radius r. And you will encounter caps lock r to represent the radius is just to represent a very big circle. So it has a big radius, of course. That's the representation of r, the big r. For the small r, for radius, it's just a small circle as well. And now, let's have our answer here. The force of gravity is still positive. Gravity is positive. So the value, square root of 9.8 times the radius in the problem, if you could still recall, it's 2 meters. And then 9.8 times 2, it's 19.6. And let's get the square root of 19.6. The answer is 4.43 meter per second as the top velocity, the minimum top velocity. It only needs 4.43 meter per second to continue the loop. Okay? And lesser than that, of course, the loop will not gonna push through, or it will go to slack. The tension will be loosened, or the strength of the tension is like losing, and it cannot push through the loop. Okay, the loop is incomplete if it's lesser than the minimum top speed of our loop. The top speed will just focus on the gravity, the value of gravity, which is we will take the positive value of it and then multiplied by the radius given. Uh-huh. So now let's continue. There's another condition here. If the engineer wants the object to successfully complete the full loop of that object without the tether ever going slack or losing tension or losing its strength, let's figure out the minimum initial speed required at the bottom of the circle. So for example, this is our circle. The bottom part of it is here, is our point, and this is the bottom part here. So we need the velocity at the bottom that is, yeah, minimum. And if we will derive this one using the conservation of energy, we will arrive to this derived formula. So 5g and an r. It's derived already. So we will be using the radius provided in our problem. If you could still recall, the radius in our problem is 2 meters. So just plug in directly the 2 meters in our equation. And our gravity, 9.8. And this time, we will substitute our values. Square root of 5 times 9.8 meter per second squared. And then multiplied by the radius, that's 2 meters. Just plug in directly and we can get the answer. Carefully plug these figures in your calculator. 5 times 9.8 times 2. The answer is 98. And let's get the square root of 98. Have 9.9 meter per second squared. Meter per second alone. This is the minimum velocity at the bottom. Above 9.9, it can complete the loop. Or above 9.9, so if the initial velocity is 10, it can complete the loop. And at the same time, if it's lesser than 9.9, of course, it will not survive the circular motion or the circular path. It will not complete the circular path. So this is the minimum threshold of our initial velocity at the bottom. So it must have more than 9.9, not lesser than 9.9 in order to complete the loop, because that's the target of our engineer here. Our engineer here. The engineer wants the object to successfully complete the full loop, and it needs an initial velocity at the bottom, 9.9 meter per second. Yeah, per second. So these are the values that we calculated a while ago. We have the top velocity at its minimum, 4.43 meter per second. So at the top, velocity at the top minimum must be greater than or equal 4.43 meter per second squared. That's the needed threshold. Equal or greater than that, it can complete the loop. Okay, and remember, this is our 90 degrees here, and let's try to assume that this is the 86 degree point of the circle where our object is having a 4 meter per second speed. Okay, and our needed initial velocity, as we calculated here at the bottom, the minimum initial velocity required must be greater than or equal to 9.9 meter per second squared. And imagine it's 4 meter per second squared going up. And as we all know, that if the velocity will go up, it will decrease its value, or the speed will go down if it will go upward, right? So imagine this 4 meter per second will reach 90 degrees and then decreasing, decreasing, decreasing. So there's a possibility that it will not gonna cross, not cross, but it will not gonna push through the motion because it's now lacking the speed as it goes up. So the tension at the same time will become lesser and lesser and lesser until it cannot make it through the top speed. So therefore, it will just follow a trajectory. Like for example, let's say for example, this is where the motion stops from this point going to this point, and our object will follow a trajectory just like that. Okay, it will fall down if ever the tension is gone in this particular motion. So I will be given an example. If the object is moving there and then it loses the tension becomes zero eventually, or if ever that there's not enough velocity to make it through. So where is the object's motion? Okay, so let's try to find out here. I will be using this circle here. Earlier, our verdict is that the object cannot make a complete loop because it lacks enough velocity to pass through our top minimum velocity, which is 4.43. Okay, now going back, so we will be practicing if the ball or if the object will just drop down like in free fall vertically, or it will fall in trajectory. Like most of the time, when the velocity is not enough to push through with a loop, it will really follow a trajectory when falling down in any point here. But we have a certain condition that the object will fall like a stone falling vertically or free fall towards the ground, and at certain specific point and condition as well. Let's say, for example, if we have an object moving from A to B, okay, from A to B, it moves here with decreasing velocity. There are tension force here getting smaller and smaller, but yeah, there are still tension forces here. So it will not gonna slack or move away. It will just like go down to its original position. Going up, not enough velocity, it will go down like a pendulum. And if ever that we have another scenario, if the object, if and only if the object will reach here at 90, and then the velocity becomes zero as an instant, so technically the object will move here like a stone drop by, or it falls like undergoing a free fall. Okay, if the condition is the velocity at an instant becomes zero at 90 degree, it could be, okay, it could be happening, but in reality, there's still small amount of momentum that will be able to push through a little of our velocity. So it will not gonna be at an instant zero, but if ever it is zero, it will fall like that. But if not, there is a certain point here. The object will just move tangentially, supposedly. It will move a little bit upward, and then it will be falling downwards, like a situation called the thrown up in our free fall problem. Okay, if ever that our object is, penetrating all the way here from A, I will use the other color, from A going to this, and then it loses the velocity here because it's increasing as it goes up. There's no enough energy, but there is still tension force here ongoing. And if ever that it breaks, the object will, well, supposedly it will move tangentially, but due to the presence of gravity, it will be falling like in a trajectory. Ever that the motion continues, and at this very point at the top, it loses enough energy, so therefore it move tangent to it a little, but then again, it will be pulled down by the gravity. Okay. And if ever object will be at the other side of the circle, so there's a big difference here because as we go down, as the object goes down, it gains kinetic energy, or it moves very fast. It moves very fast. So therefore, if the object is from 180 degrees with respect to the bottom, it will go down here. There are still tension in here. And if ever the tension will break, for example, no enough, or the tension here becomes zero, the object will fall tangentially, let's say at this point, tangentially. But then again, it will move in a trajectory because of the presence of our gravity. That is something that I want you to know, that in a physical sense, when the object will stop due to not enough velocity in any point, yeah, technically speaking, if that object will drop at that particular degree, it will follow a parabolic path or a trajectory. It will just go down like a rock, falling downwards directly if ever velocity becomes zero at an instant, especially at this point here, 90 degrees. Okay, at that point, the object will definitely move upward and then fall downward, moves upward and moves upward and falls downward due to the gravity. Okay, but technically, in most cases, it will follow a trajectory. And please remember that. And if our object is here and it lacks enough velocity, it will still be, if the tension is still here, pointing towards the center, it will push through up to the original or the starting point because the gravity will pull it here, will help in pulling it. It will not break away. It will just continue to be at the bottom, increasing its velocity. That's it for today. I hope you enjoy and you understood something here. Thank you so much and see you around in my next video. Bye for now.